Hey everyone, in this AP Chem series video, we're going to continue taking a look at the periodic trend in first ionization energy. First, let's remind ourselves how this first ionization energy changes across a row, in general increasing from left to right. This is because within that row, the outermost electrons are all in the same energy level, but the effective nuclear charge does increase towards the right-hand side. This causes a greater attraction between those outermost electrons and the nucleus, making the electrons harder to remove, so we observe higher first ionization energies like phosphorus's 1000 compared to sodium's 500 kilojoules. In this video, we'll take a look at how this first ionization energy changes within a column. So to analyze this trend within a group, let's focus only on oxygen's column. You can imagine moving from top to bottom. We'll start by taking a look at oxygen's nuclear charge +8 and its full electron configuration. We don't need to write out this model for every single atom in the column to see some of the patterns here. Let's just do it for sulfur and selenium. So here's some things to notice. First of all, I can see that the nuclear charges of these atoms increases dramatically, but along with that, so does the shielding. To really get a sense of the positive charges at work inside these atoms, let's calculate the effective nuclear charge of each. Oxygen's +8 nucleus is shielded by 2 core electrons, so the effective nuclear charge experienced by the outer electrons is only a +6. If we do the same thing for sulfur, you'll see that its +16 nuclear charge is shielded by a lot more electrons, 10 of them. Factoring in those 10 shielding electrons means that sulfur has an effective nuclear charge equal to oxygen's, +6, and if you do it for selenium, you get the same result. So within a column, just like we've seen before, the effective nuclear charge remains constant. That means we can't use it to explain any differences in ionization energy. So if we can't use nuclear charge, let's instead look at those outermost electrons and where they are. Here in the second energy level, sulfurs are in the third, selenium's in the fourth. As you move down that column, the outermost electrons fill to higher and higher energy levels. What's so special about that? Well, if they're in higher energy levels, that means they're farther from the nucleus. That means they're going to be less attracted to the nucleus. That means they're easier to remove, so as you go down that column, you're going to get smaller and smaller first ionization energies. To prove it, here's the actual values for these 3 atoms. Oxygen's outermost electron takes 1,300 kilojoules to remove, sulfur's is less at 1,000, selenium's even less at 941. Let's summarize these ideas first by saying, in general, your ionization energy decreases from top to bottom within a column. Even though those nuclear charges increase a lot, the increased shielding cancels that out and keeps the effective nuclear charge relatively constant. That means the changes in ionization energy are because those outermost electrons are in higher energy levels, farther from the nucleus and more weakly attracted to it, makes them easier to remove, and we get lower first ionization energies. These are the key ideas for the video. Make sure you take a minute to pause and write them down. Moving forward, you will probably be responsible for remembering the overall trend in first ionization energy. A nice bar graph visual like this can help your brain to remember that the atoms in this upper right-hand corner have the highest ionization energy values. Or if you're taking notes, draw a quick schematic of a blank periodic table. Have one arrow pointing up, labeled with increasing first ionization energy. Draw a second arrow pointing left to right, labeled with increasing first ionization energy, or simply label the top right-hand corner as the atoms with the highest first ionization energies, and the bottom left-hand corner as the atoms with the lowest. I recommend jotting down this version. You can pause and take a moment to do that. So those are the general trends, but like always in chemistry, there's lots of exceptions, and you might already know about some of those. A common one is the increasing trend across this first row is true, except for a slight decrease between nitrogen and oxygen. The good news is that as of 2020, the AP Chem exam shouldn't ask you about why those exist, so we're not going to cover them in this video. And that just about wraps it up. Thanks for watching, and here's a brief summary.